Accepting people.
Hello, good morning. Hello, good morning. Good morning, good evening. I don't know.
Lots of time zones.
Hi, Simi. Long time.
Hi.
Long time no see. Oh, Gary, long time no see too.
Yes, Sue-Ming. I was going to stay very quiet. How are you, sir?
Oh, good. And you?
Yeah, no, I'm good. Still
What's the
enjoying.
time in Wellington now?
10 p.m.
10 p.m. Oh, so that's not too bad.
No, very leisurely time. Very good time.
It's okay. No, it's okay. What do we have here? Okay, hello everyone. I think we're good to start. Thank you for joining us today. I see that Mohammed and Said also joined the call. So for today, I think Mohammed can say more about that. We have a discussion planned on conformal prediction by Mohammed. So Mohammed, whenever you're ready.
Yeah, I think we have maybe a good. Hello, everyone. We have a few members. Maybe we do some presentation before that, and then maybe we can start the paper discussion. Maybe. I think Xiu-Ming joined us lately, so maybe Xiu-Ming, if you can say something about yourself.
Okay.
Are you recording, Amelina?
Sure.
Okay.
Yes, it's being recorded.
All right. Thank you, Mohammed. My name is Xiuming Tam. I was the chief methodologist of the ABS between 2011 and 2019. And before that, I was working as a general manager on many different subject matter areas: population censuses, population surveys, demographic statistics, classifications and standards, transformation program. So basically, most of the official statistics work on the social side and also on the data management side I was involved in. But my last 8 years was on methodology, and I published about 50 plus papers in peer review journals. So I am very interested to take part in this. In fact, I worked with Inkong a few years back, and we did a joint paper as a result of a piece of work by another committee set up by HLG Moss on, I think the name of the paper is something like statistical or quality framework for statistical algorithm. So I can see that this work arising from this group could potentially be another paper published by UNECE or even a journal paper. So I'm really looking forward to it.
Yeah, thank you very much, Xiuming, and welcome. Is there anybody else maybe who joined? And I see Gary is here. So Gary, maybe you can say something about yourself because maybe some of the guys do not know you.
Hey. Hi, my name's Gary Dunnett, and I'm currently the Deputy Chief Methodologist here at Statistics New Zealand. But I'm sort of attending tonight's session as I'm the chair of the Applying Data Science and Modern Methods group within the HLG MOS, which is one of the work streams that's working under the group that I chair. So I thought I'd just come along and support you. Listen to the work, and then this is probably the only. I'll try and attend other sessions, but this is I'm just an observer really, but also I like learning. I do have a couple of my colleagues, a couple of my staff participating in this group, so they're much better at it than me.
Yeah, thanks, Gary. Anyone else we missed? Maybe who joined just today or lately? Okay, I think we're okay. So yeah, so hello again. So last time we agreed, team agreed to start to kick off this work with a paper discussion, and oh, I see Farida maybe is new also. Farida, can you say something about yourself? I can see you here. Okay.
Yeah, hello everyone. So I'm Farida Begum and I work for the Stats New Zealand. So Gary is like the chief methodologist in that branch. So I'm kind of working more than 2 years in the stats department with the household survey and data integration team. And before that, I did a short-term postdoc in data science and the PhD. Thanks.
Thank you and welcome. Welcome. Yeah.
I might just for completeness introduce myself as well. I'm also from Stats New Zealand. I'm Andrew Martin.
Yeah. Welcome and nice to meet you all. Thank you. Thank you. Okay, so yeah, we can start. So last time you said we wanted to do a paper discussion, the gentle introduction, and some of you proposed the gentle introduction to conformal prediction, and then I think I wrote on the wiki I might do a presentation. I think I committed I shouldn't, but anyway, so it's up to you. We can maybe go through the paper, or I can share maybe a presentation as I started, and we go from there. So maybe yeah. Okay. So let me just try to share my screen. Okay, just give me a second, please. Share. See. Okay, can you see my screen?
Yeah.
Okay, thank you very much. Yeah, so last time we agreed to do a paper discussion. Okay, this is a long paper. We cannot cover everything today. Please do interrupt me because I cannot see the raised hands, or Amelina, just let me know that there are questions in the chat or somebody raised their hand. Okay, so I wanted to do, I started just very simple, maybe PowerPoint, not I worked on it mainly yesterday and the day before, but hopefully we can cover some basics and agree about certain notions and see what are the strengths and weaknesses of these methods. And then we can go from that foundation, we can go maybe in the next meetings, dive deeper into this field. So yeah, so I'm gonna talk about conformal prediction. We'll start with conformal regression in the paper. They start with the classification. They worked a lot on classification and images. I think I find it natural for us statisticians, especially to look at regression first and talk about residuals and then go to classification, which we don't do much. And then I will cover a little bit of classification. I will always go with the baseline method and then try to improve that method. So in the regression, I will do a baseline regression, and then I will try to see how we can improve that baseline CP, the baseline conformal regression. For example, by doing quantile regression, conformal quantile regression, and then there are more improvements for that method. And same thing for classification. I will present a baseline CP, and then I will talk about adaptive CP, and then this is an improvement, and then adaptive CP has some weaknesses. Maybe it is adaptive, but the sets are sometimes large. So there is another technique, which is regularized APAs, which aims at solving some of the weaknesses. So we go like that, okay? And there are some topics I might not cover today because we won't have time. So this is kind of the plan. At the end of the presentation, I have also a lot of, I have an appendix with a lot of material also. We might, if we need that material, I have added to the last one. Okay, so what is this conformal prediction or conformal inference? So this is from the paper. I just picked it from the paper. So usually we have a prediction problem. We have an algorithm or a model. Model predicts a point estimate or a prediction, point prediction. And what we would like to have is a kind of interval or set around this prediction to quantify the uncertainty. And it's very important for decision making. What is this conformal prediction promising is that the guarantee, we're talking about the guarantee, the coverage, we can have that for any model. You know, whatever the model, I can always have that guarantee. I'm not saying that the interval of the set is going to be small or have very good properties, but at least the coverage. I'm guaranteeing the coverage, you know, assumption free on distribution, finite sample size. For me, for a statistician, this was a surprise. And first time I met this CP, I said, this is too good to be true as a statistician. And then I dived deeper to see how come we could obtain all these with very minimal assumptions. Yeah. So this is CP, also known as conformal prediction, user-friendly framework or paradigm, statistically rigorous prediction sets is very important for us statisticians. You can use it with any pre-trained model, such as neural net. Take your black box. You don't understand how the model, even somebody else developed that model, but you can always assess the quality. Yeah, easy to understand, and you can apply it to different fields. You know, supervised, unsupervised, reinforcement learning, etc. So basically, this is in the introduction. I just picked it there, and here you have also a slide from Michael Jordan. I will invite you to go and have a look at his web page. This guy is a giant in statistics, you know, and the authors of the paper, Angelopoulos and Bates, they were or they are still Angelopoulos, his students, you know. So Bates was with Candace, you know, in Stanford, PhD with Candace, did his postdoc with Mike, with Jordan, and Angelopoulos is doing or finishing his PhD with Michael Jordan. So this is a very strong statisticians, whereas maybe Angelopoulos and Bates are more machine learning practitioners, or but very sound statistics. Okay, so I think this slide maybe one of the most important slides, and this summarizes really what we are doing here. So what do we want? So our goal is to construct or build a prediction interval. So we are doing predictions here. Okay, there's estimation and there is prediction. We are doing prediction, and usually we build intervals or sets. Okay, so usually in classification is sets. This means a set of images or classes for plants, for animals, for or could be industry codes, for example, and intervals could be intervals or union of intervals also. Okay, so what do we look as statisticians usually or scientists in an interval? So there are certain properties we seek in an interval, and this is very important when we discuss this type of topics and the promises of conformal prediction. So the most important, in my view, is validity. What is validity? You want your interval, you want a guarantee of coverage. You want your interval to cover this unknown parameter that in our case is a future observation that I want to predict a y. I want to predict a y. So this is our theta here. So the most important property is coverage, and it's called validity. I want my interval, my inference to be valid, and CP gives you this. CP gives you number 1. What CP does not give you automatically is 2 and 3. So 1, CP gives me 1, okay, but my interval could be large, my set could be large, my set could be not adaptive. The second property I look in an interval, prediction interval, and even in confidence interval is efficiency. Okay, so I want after I secure the coverage. Usually, on average, it's probability, frequentist paradigm. This is how you read it. So I want that interval to be as small as possible. So I want to be sure that I cover, and I want this interval to be meaningful, informative, for me to take a decision. This is mainly for decision making. And the third one is adaptivity. Okay. So, and usually local adaptivity. So I want my interval or my set to be adaptive. For simple cases, clear, simple, I want it to be small to tell me, look, I'm sure. For difficult cases, I want it to be large and tell me, look, I'm not sure here. There is variability, I'm not sure. And I have here 2 examples, one in a regression and one in classification, a regression on top, classification on bottom. So for example, for this one here, and it is, I think this example is from Tipshirani's paper, and I shared it with you. So here we applied the split CP, split conformal prediction. Of course, if we have conformal prediction, we have guarantee. So number 1 is done. So left panel here, the red, in red, I have fixed width. If I use the vanilla flavor, the baseline CP, all the intervals are going to have the same width. This is a regression. I have just an X and then Y, just, unidimensional here, univariate. I have X and Y, and I use X to explain Y, and I have a function here in the middle. And of course, I predict that function, and here you have like 1,000 points. We will see that later, but you have 1,000 points. These are future points, a future. So I have 1,000 X values. I'm predicting 1,000 Y values. For each one of those Y values, I am constructing a prediction interval, and I put those prediction interval one next to each other. So it looks like a band, but it's not a band. These are like 1,000 vertical prediction intervals. So this is CP, baseline CP gives you this. So you have the coverage, but it is not adaptive, Whereas the right panel, and here we will see later, for the score function, we use here, they use the residual only. Your error is the residual, whereas on the right side here, the blue one, for the error score function, they use the standardized residual. So you divide by an estimate of the variance. So if the variance is large, then your interval will be large, and if the variance is small, your interval will be small. So here I don't want to have very large interval. There is very small variability, and I want my procedure to catch that. Okay, so we have vanilla flavored or baseline CP, and then I know that I will improve CP. So I'm looking for these. CP, there is a paper, I think Gamerman and so somebody, there's a paper where we can show that CP obtains on average, is the expectation of the length of the interval, on average, small intervals, on average, okay? So CP has this also, okay. So this is good. And for classification, same thing, apply CP. We have guarantees because we are doing CP. We have coverage. And I have 3 pictures. This is my X. The picture is my X. Okay, these are the X values. And for this picture, I want to predict the label. What is this? So I have like 1,000 classes. I have animals, I have airplanes, I have plants, I have cars, bicycles, etc. So I have this picture, which is like my input, and I want a label for this picture. What is it? I want the model to recognize this. So by using CP, here, for example, I have very clear, simple case. CP provided a very small interval, which is a singleton in this case. And for this picture here, for this X, and I have 1,000, let's say 10 classes, it will give me probability for each class. Probability of a squirrel is 99%, probability of a cat is 0.001, probability of a dog 0.00 something, and so on. The sum of the probabilities is 1, but the highest probability was given to fox squirrel. Okay, so in this case, you can see that the sets are adaptive. For simple case, it's small, like here, and here the model is not that sure. It assigned 82% probability for fox squirrel, for gray fox 0.03. Anyways, when you sum these probabilities, usually you have more than 90% because the target here was 90%. Same here, if you sum them, you have 90% or more. And in this case here, I'm not sure. Sorry. In this case, I'm not quite sure if it is really, but it's more probably a marmot, So yeah, so this is what we are looking for, these 3 properties, and CP guarantees the first, and on average, CP gives smaller intervals. So we know that. Good. I think we've seen this. Yeah, you have a question?
So may I ask a question on the classification of the 3 pictures? So the confidence interval is not, we normally consider as a confidence interval where you got a lower band and a high band. Here, the confidence interval is in the middle case, the medium case. The confidence interval comprises 4 potential labels.
It's a prediction set. We call it a set. In this case, we call them set. It's a prediction set in classification because these are discrete. Yeah. No, they are discrete. Yeah.
Mm-hmm. So a prediction set.
Yeah, it's a prediction set. Yeah. And in statistics, we don't do a lot of classification, but for example, we do industry. Industry, we do, for example, classify for industry. We do, yeah.
Yeah. I think in the official statistics example, your pictures would be text. So like collecting information on occupation in a census.
Yeah.
So in Australia, we've got 28 million people. So we've got 28 million, not 28 million, probably 14 million text on description of occupation. And our label would be to say whether that description is a data scientist or a statistician or a GP. So we do classification in that sense.
Yeah, very good example. Yeah, thank you. Yeah, we do a lot. Classically, you know, we do in industry, a lot of industry, but as you said, next, yeah, you have a description of your industry or, yeah. So thanks. So yeah, so
There's another hand, Mohammed.
Oh, sorry,
Lorenzo.
Lorenzo.
Thank you. Yes. If you could just go to the previous slide. Yes. My question is the number that I see under the Y. I mean the categories in the sets are the score returned by the algorithm. But are real probabilities or the probabilities returned by the algorithm, like the softmax?
Yeah, a very good question. In fact, people call them probabilities. They are not probabilities. Okay, these are the softmax scores.
Okay.
And for those maybe who are not familiar with this, you have an algorithm, and this algorithm, of course, it's like for logistic regression. Yeah, I want to predict 0 or 1, but my logistic regression doesn't give me 0 or 1. My logistic regression gives me probability of y equals 1. And with this type, if that probability is greater than 0.5, for example, or a certain other threshold, I decide it is 1 or I decide it is 0. Same thing here. The model gives me numbers. A1, A2, A3, A4, positive number, like exponential something, for example. So it gives me numbers. Those numbers could be 300, 3,000, etc. So, and then I standardize those numbers, A1 over the sum, A2 over the sum, A3 over the sum. So now these new numbers are between 0 and 1, and when I sum them, it's 1. People call them probabilities, but they are not probabilities. They don't relate to any real world probabilities, but we call them probabilities. So usually in machine learning, when you get those probabilities, because for this picture, I have 10 classes, and I'm gonna give probability for each one of these. I call them probabilities for each one of those classes. So for squirrel, it gave 99%, the softmax, but for the other classes like dog and cat and airplane and bicycle, it also assigned the probability, maybe 0.0001. No, and when you sum all those probabilities for the classes, you got 1. Okay, so this is how it works. So usually
there is no constraint that the sum is over 90%. I mean, usually it usually is, but it shouldn't really. There is not a real constraint. That's correct, or?
Yeah, because it is how we did this thing here. So this thing, they used CP, but they didn't use the baseline CP, and they use APS, the best CPs. And the best CP is you sum. We will see it later. It is like you aggregate your probabilities and until you are greater than 90%. Yeah. So it's
Mohammed,
yeah.
I did not read the paper, but I actually watched the introduction of this concept by the two authors on YouTube. And if I understand what they're saying correctly, in relation to the question asked by the last gentleman, the interpretation of those intervals are, if you look at the medium, what they're saying is that the probability of the right label in that class comprises 4 elements. The probability of the right label in that class is 90%. So that's how they interpret that interval. So for the hard one, there are 5 elements or 6 elements. So the probability of the right label in that class of 6 elements is 90%.
Yeah, it's at least 90%. Yeah.
Yeah, so that's quite different to our normal interpretation of intervals in classical statistics.
Yeah, this is a set, so it's yeah. We're going to see more details about conservative about this in a moment. But thank you for. So I'll go very briefly here. What advantages, what conformal predictions give us? Guarantees coverage, okay. And model agnostic, it means whatever your model, and I don't care, I don't know what your model is, it's black box. I can always build those prediction sets or prediction intervals and guarantee coverage. This is what it is saying. It's not saying that those prediction sets or prediction intervals are going to be small, adaptive, or if you have a bad model, your scores or your residuals are going to be large. If the residuals are large, the quantile is large, and then your prediction sets are large. So yeah. Distribution tree, we don't put assumptions on the distribution of the data, except for the calibration and the test. We assume them exchangeable, not even IID. This is beautiful, finite sample size, no asymptotics here, and goes to infinity, normal or something like that. So there is no assumption, finite. You don't need to retrain your model to do this, which is beautiful. And then you have broad application, okay? So I'll go a bit fast here. There is some repetitions in the slides because we wanted the gentle introduction and follow. So this is a high level outline of split conformal prediction because we're splitting the data, training, calibration, test. So we assume we have a calibration data. So you have data, you used it to train the model. This is new data that the model didn't see, and you have a new point. You know the auxiliary information, you don't know the label for which you would like to predict this label in red, which is unknown. We have an algorithm, I'll call it A or call it F hat, anyways, takes a sample and gives you a function. And then this algorithm will give me a point estimate, Y hat. Okay, so I get Y hat. So we don't want just the point, we want an uncertainty around that. And the only assumptions is that there's exchangeability and they come from the same distribution, these guys, the calibration and the test. And okay, and what we want is this. I'm gonna give more details later. Okay. So what CP is giving me is that given the calibration data from this distribution, they are exchangeable with the test. All of them, when I add the test, the whole thing is exchangeable. I have an algorithm, whatever the algorithm. I have a new point from the same distribution. And this, I assume that xn plus 1 and yn plus 1, this data point and the other data points here are exchangeable. And I want to produce a confidence set. You see, I'm putting an index here. The length, the quality will depend, of course, on your data, will depend on algorithm, etc. But the guarantee, I will always have a guarantee. And this is beautiful because what we are talking about is the left-hand side. When you have equality, you say this is 90% exact coverage. And here we have like greater or equal to that 90% or 95%, whatever you choose. We're going to just use the example of 90%. And this is called conservative coverage. So I have more. What I like here as statistician and mathematician, I like this thing here, is that I have coverage. I know that the probability that on average, my intervals on average, they are gonna, it's 90% probability to cover the unknown. So probability for the interval to cover is more than 90%, but I have an upper bound, and this upper bound is telling me while your probability is greater than 90%, your set, I'm putting a bound on your probability. It's like saying I'm putting a bound on your set. I'm not allowing your set to be too large. So this is beautiful. See, for example, if n equals 99, if you have 99 extra future and 99 extra in calibration, in 99 pictures, and then the probability will be between 90% and 90% plus 1%. So the probability is squeezed between 90% and 91%. So this is beautiful. The right-hand side is also beautiful. So because CP, we always think about this. That is giving me this. There are conditions for the right-hand side, which is some the data continuous, because there are tricky stuff here we are not mentioning, which is you could have ties. You know, there's things in statistics that we don't like and we have to deal with. You could have ties, so you have to deal with that. Anyways, but it works. I'm going too fast here. I'm seeing the time. I want to cover a lot. So guarantee coverage, the size and adaptivity will depend on the distribution. So the coverage I have, but the size, small or not small, adaptivity will depend, of course, on the distribution, will depend on the algorithm, etc. So if the distribution is nice and the algorithm is smart, good algorithm, then this should be small. We will see later because the residuals are small. When you take the quantile of the residuals, if there is small numbers, the quantile is small. So when you take new one and you want it smaller than the quantile, there are just few of them smaller than that quantile who is small. So your set is small, okay? Or your interval, depending. So it depends on the distribution and the data. We don't need IID. We assume just exchangeability, which is also something incredible, you know, for us. But you can think about them like independent and identically distributed. So, and what is important, this assumption is not only on the calibration set, but on the calibration and all future data points. Here we are assuming just one future, but I could have 1,000 future. You see these intervals when I had that red band, we had 1,000 new future data, okay? Of course, this is trivial. If you are not looking for size or efficiency, I can always give you an interval with exact 90%, with exact 1 minus alpha. I can always give you that. So if you don't put that restriction or constraint of size, so you can always, whatever problem you have, you can always build a 1 minus alpha prediction or confidence interval, always. But might not be good, you know. And the probability is over everything, okay? This is very important. This is marginal, not conditional, okay? So this is marginal probability.
Mohammed?
Yes?
Yeah, I have a question about this calibration set. So, okay, maybe this is a wild idea, but do you think this will work for some synthetic data?
What do you mean synthetic data? I mean, if all you have synthetic data, you build a model and you have calibration data, or?
Because if we are looking at kind of a text classification, like industry or economy activity, and some of the classes it's a typical problem to have what do you call this a non-representative. So some of the classes have so few examples. So some organization wants to use like generative AI to create a synthetic data. And I was wondering if this sample X1 to Xn, it says we don't need the IID assumption, just exchangeable. It just got me wonder, would it work for synthetic data that didn't see the model or wasn't involved in the model creation?
What you need is, imagine you have data and you want to build a model. You have data, and I have I take 80% of my data because there are assumptions here. Of course, you need the representativity and the representativeness. Otherwise, you can't work. So you have a sample, and I am assuming we did a reasonable job by having a representative sample, etc., or stratifying, etc. So I take, for example, I take 80% of the data to build the model and 20% of the data, and they are both represented samples. I split them, and 20% I put it in the calibration. So those calibration data are supposed to contain all the classes, are supposed to be a representative sample. Because if I have in the calibration data just cat, I have just pictures of cats, and I'm not presenting all the other categories in my population. Let's say my population has cats and dogs, and I have just pictures of cats, and then it's not going to work here, for example. It's not going to work. So the calibration set is like a sample from your population, but very small. It doesn't cost you a lot. The majority of your sample, you use it for modeling, and then this sample. I don't know if I answered your question, because if you say we don't have enough classes and you have to generate extra data. I'm assuming that when you generate the extra data, you are using a certain distribution, that data comes from the same distribution. Because otherwise, why do you create synthetic data that do not, usually you don't have the constraints of having the same distribution. Usually we put a constraint of having the same distribution. It's not perfect because you have multidimensional, maybe you use just 10 variables. I say same distribution like this 10, but there are more variables, so you are missing. But in general, these guys come from my population and they are like representative, so I need to have enough of. I don't know if I answered your question. Or...
Income.
Yeah, actually, it was about in the case where you don't have even enough sample to construct the calibration set, like when you just don't have enough data and you want to boost your data, so it's kind of a resampling, but you create from outside your data set. Yeah, maybe we can.
Yeah, there is a risk. There is a risk. Because I have an assumption that these guys come from the same distribution,
Yeah. There are actually two ways of increasing the sample size. Mohammed used the example of having a 20% in the calibration data set, and the training data set is 80%. So you can look at dividing your they call it cross validation, CV. And I think in this case we're dividing into, if you like, 5 sets of 20%. You use 4 sets as a training, and the other remaining 5th set as your calibration. But you can use the 4th one as your calibration too. So that's cross validation. Another way I think Mohammed is right that we need to simulate in such a way that we reflect the underlying distribution. Bootstrap is another way to do it. So you got your 100% data set, and then you can bootstrap that. When you bootstrap that, you're actually reflecting the underlying distribution. And then you apply cross validation again. So you can do it multiple times, I think.
Yeah, when you do modeling, yeah, exactly. This is the assumption, is that I am assuming that these guys, that the calibration and the new test come from the same distribution. That's the assumption. So if you are perturbing the distribution, then you are putting a new assumption by saying it's approximate and I live with it and I'm going to use it as if it came from PXY. This is the risk you are taking. But this is an assumption of working assumption here. You can have something approximate. It's okay. You can have something approximate. Okay.
Mohammed, we also have a hand in the chat. Pier Paolo, please.
Pier Paolo.
Oh, thank you. Thank you. Yes, may I ask you a question? If understood well, the data exchangeability is a fundamental property of the CP. But this could be problematic in case of large scale data sets coming from different sources. And how can we test for it? is there any tests for assess the data exchangeability? Because okay, I don't need to say that they are IID distributed, but data exchangeability is fundamental for constructing a training set, calibration set, and test set. But when data are coming from heterogeneous sources, this could be problematic. So
Yeah,
maybe
right.
we should think to a tool to test for the data exchangeability to find similar. I think that CP works if I'm dealing with similar records, for example, in a large data set. No? Similar in the sense that they say the same thing. They are the same profile of person of an individual. If this don't happen, maybe the CP could result in large prediction sets, so unreliable.
Yeah, exactly. Let's look at that. I have jotted it down. Let's look at that. But there are papers, and we will see later, there are papers with CP beyond. There is a paper called Conformal Prediction Beyond Exchangeability.
Okay.
Imagine you have time series. Then you cannot say they are exchangeable or independent. It's a time series. They depend on each other. So you say in time series, I cannot use CP, but people found a way to use CP for time series. So you have CP for time series. There's always, you need just to find that heuristic notion of uncertainty. How do you do it? So there is a paper, Conformal Prediction Beyond Exchangeability, one. I think you can find it in the references of this paper, or you can just type conformal predictions beyond exchangeability. And then CP works for time series. CP works for, we will see, for distribution shift. So what happens is that it could happen that your future data, that the distribution of X is different from the distribution of the X's here. So you could have feature shift. The distribution of X could change. The distribution of Y could change. But the distribution of Y given X could be fixed. And you could have even the distribution of Y given X. We were hit with COVID. You have a time series or you have a model, you build it before 2020 March, and you want to deploy your model, and then COVID hit, the industries went down, a lot of them, distribution changed. How do you do? You cannot use your model, and you have just 2-3 months of data. You cannot build a new model. You're done. So, but you can use the old model, assuming the distribution of Y given X didn't change, even if the distribution of X and Y changed, and you can calibrate using that model. We can talk about it later. I'm just seeing the time, but this is good discussion. I have jotted it down, okay? And and this thing here, you're welcome, Pierre.
No, thank you. I will read it.
Pierre Paolo. Yeah, thank you.
Thank you.
Okay, so this is what I said before. You take data here, and you use it for training the model. So this data, the orange, you divide it into test, validation, and train. Here you can do cross validation, etc. This guy is not your test. This guy is new, has nothing to do with the test who is here. And then there is a new, we call it test, okay, terminology. So this is the future data coming. I have a new text. What industry do you put? And this is the industry. Are you certain about it? So I go very fast here. CP, you train. There is step which is training. You put some calibration aside. You train your model on training on the orange. Calibration is the blue. You compute uncertainty scores or non-conformity scores on the blue, and you have them here. You choose a miscoverage or alpha, and or equivalently, you are looking for 1 minus alpha coverage. You compute the quantile, 1 minus alpha quantile. Now we do this thing here. They do this thing here. This is finite sample size correction. Okay, it just gives you, if you have 100, if I had a continuous distribution, I will cut at 1 minus alpha, I have the whole distribution density. But here it's final sample size, we have quantiles are tricky. You need to take a little bit more to be sure that you have the thing. So this is, think about it just at 1 minus alpha quantile. You just correct it a little bit. This is the ceiling. I'm taking the guy a little bit larger and divide. So this is the empirical quantile, not perfect. And I take that empirical quantile and it is just the n plus 1 minus alpha ceiling smallest. So when I order them, I take this guy in this order. Okay, I got calibration. I have my Q hat. I'm ready. Now give me a new xn plus 1. I don't know the y. I take this guy and I use all the y's in my classes, for example, classes or industries. And if it is continuous, it's a y. And then I compare it to Q hat. If it is smaller than Q hat, I add the y to the bag. If it is not, I don't add the y to my prediction set. And that's the prediction set. So this is just very simple. I'm just repeating myself. And this is what they say in the paper. And I put something about non-conformity, just a repetition here. Okay, time. Okay, it's a very important thing about marginal versus conditional coverage. As you know, conditional coverage is this. This is from their video. So we don't have this. I don't have the probability of being in the set. Or sorry, the probability as a statistician, the probability of the set covering, the randomness is in the set. The probability of the set of covering y given x, I don't have that usually, because usually this is what we want. I want my doctor to tell me what is the probability of me maybe in the future having colon cancer given my data, history in my family, my age, etc. I want you to give me that prediction for myself, not for the average Joe, and that's what I would like to have, because that's the important thing. We cannot achieve this. You will see in the slides later on in the paper. We cannot achieve this usually. It's almost impossible. We can be very close to it and sometimes really nail it. But what we can have is something called group conditional. So I could have what is the probability of the probability of the set given that I am in a certain group. For example, age group, salary, bracket, geography. For a group, I can do that, okay? So this is bad news, but there is good news. And the good news is that if I use the baseline CP, I might not get this, but there are improvements to the baseline CP that will bring me very close to this. So if I'm doing a regression, then your friend is conformal quantile regression. And then I take quantile regression and I conformalize that quantile regression, and it will be really very close to this. It will be adaptative and small. If you are in classification, the baseline won't give you this, but if you do adaptive conformal prediction, APS, then you will be really close to this. Now, on my left side here, we have 3 examples. We have an example of no coverage, difficult, CP in the middle, and then ideal from left to right. And imagine you have data here, you have a curve, and you have prediction intervals here, vertical. You put them together. It's not a band, it's prediction intervals. You put them together and you have the yellow bands, lower and upper bands, and you have your data. Maybe the drawing is not good, we don't care. But imagine that in these dots here, there are 2 groups, group 1 and group 2. Geography, whatever, gender, whatever you want. And group 1, the coverage is just 5%. Group 2, 14%. So maybe on average, for the whole population, the coverage is 10%. Very bad. So you can call it no coverage. So this is bad. I use CP, I get marginal coverage, our CP. But it could happen that for one group, I am perfect. And for the other group, I'm making most of my mistakes in group 2. And this is dangerous. You see, on average, I have 90%. Assuming, you know, on average, this is perfect just for the example. So on average, my CP give me 90%. I'm covering 90% on average. Okay, I'm covering 90%, but I'm doing very bad for one group. And this is very important in machine learning and in fairness in machine learning. Sometimes your model, you have MAPI, you have root MSE, whatever, it's very small. In classification, you have 99% accuracy. You say my model beats all the other models. It's a deep learning model, it's perfect. So the overall accuracy, the overall performance is very good. But when you take your model for a subgroup, a minority, people with a very rare disease or small minority, and for that small group, you see the accuracy maybe 50%. So that small group is minority, 1% in the population. And for that 1%, you are not doing good. But the overall is good. So this is what I don't want this. You know, I don't want this because I'm not being fair for this subgroup. What conditional does is wherever you are, whatever X you gave me, whatever X, and in particular, whatever group, wherever you are, I can have 90%. And this is what we would like to have. And this is what conformal quantile regression and adaptive prediction sets get closer to this. And you remember that thing here I showed? This is just by changing the score function. And I'm becoming really adaptive here and maybe small. Okay, so this is considerations we have to think about. And yeah, so think, yeah. No, I'm gonna skip this. I'm gonna skip this. I'm going just 3 minutes. So this is the algorithm. No. Conformal prediction. Yeah, this is full conformal prediction. So we did split conformal prediction, but ideally we would have done full conformal prediction. Usually we cannot because it is very costly and prohibitive. I mean, you can't. What is full conformal prediction is that you have calibration, you have a new test, and then for every value of your classes, for each class, or if you have continuous, you are in regression, for each value of y, which you cannot do, you know, it's continuous, you know, infinite, non-countable, you can't. So what you do, you discretize, like you have an interval 0, 1, you discretize 0, 1 into 100 points. And for each one of those points, you need to train the model. So you take your calibration plus xn plus 1 and one of those y's in the discretization. And for this y, maybe there are 1,000 of them, you build 1,000 models, you compute your score function, which is the error. This is one choice, guys, one choice. Just call it S. You order them, you compute the quantile, and then you repeat. And then at the end, you repeat this for each value of y. And at the end, your set, you take all the y's where the error of the y given xn plus 1 was less than the corresponding quantile. And I cannot imagine I have fully trained a deep learning model, especially for classification of images, etc., and text, NLP. You're not gonna rerun a model 1,000 times. Sometimes your model can take days to run, so take hours or days to run. So this is prohibitive. So that's why people do not do full conformal prediction. They do split conformal prediction. So there is a cost. We are not perfect, but we are doing well. Okay, we are doing okay. So this is it. Another thing I want to mention that we did not mention, as statistician, we know if you give me a confidence interval or prediction interval, if you give me a confidence interval, there's duality between confidence interval and test. So we know it as statisticians. So if you give me a confidence interval, I give you corresponding test. If you give me a test, I can give you with the rejection region, I can give you the confidence interval. So why I'm saying this, CP gives us rigorous confidence prediction intervals or prediction set. So CP is also giving us rigorous tests, rigorous p-values. Don't forget that. So CP is also, you can also say CP is doing something in the test, okay? So this is good. I don't know if I have its time, so I don't know if I have. I think we should
Mohammed,
stop.
we can continue next meeting if you want to finish it fully without rushing it.
I think next meeting, Xiuming wanted to present something. Xiuming, you said you wanted to present like Bootstrap something.
Yeah, I want to perhaps give an alternative approach. I personally, I hope I don't annoy anyone by saying this. I don't really find conformal prediction really useful for official statistics. I'll just give you an example, right? If we got 28 million occupation tags, we are predicting 28 million occupation classifications. So in official statistics, once you've done that, you say that there are maybe 10,000 statisticians. So the information, the uncertainty we want to provide is that of that estimate of 10,000 statisticians, what is the confidence interval? What is the 95% confidence interval? Is it from 9,000 to 11,000? Or is it from 8,000 to 12,000? The conformal prediction is useful when you're only predicting maybe a point, right? So if someone goes through an MRI to detect whether a person has prostate cancer or not. So I think it would be useful to say that looking at the picture, and you've got a training data set, you've got a calibration data set. Looking at that picture, you say that the chance, the prediction set is cancer, 90% cancer. But if your prediction set is cancer, no cancer, 90% is not very useful. The problem with conformal prediction in official statistics is that if you're predicting a text which is not very well described, so you've got a prediction set of this may be a statistician, this might be a data scientist, this might be a GP. For us, we would have to assign a value to that text so that we can actually produce official statistics. We can't produce 3 sets of numbers. One set is, a statistician here. Another set is a data scientist, and another set is a GP. So I'm actually wanting to propose a different approach, which is that if we use machine learning methods to produce aggregate statistics, I want to provide an uncertainty on that number. Not on an individual case, but on an aggregated number.
Yes.
Yeah, fair enough. That's why
in a lot of ways, in a lot of ways, this is no different to sampling. So sampling, you got a sample, say a 5% sample of the population, and you got a statistics from the 5% sample, say statisticians. From your sample, you got a 1% sample, you got 1,000. So you gross it up. So you say, because it's 1%, 1,000, so the population is 100,000 statisticians. But what's the uncertainty associated with that? You'll say 95% confidence interval is between 8,000 and, 100,000, 100,000 would be 9,000 to 11,000. So you want to provide that sort of uncertainty. Similarly, for statistics generated by machine learning, like coding. By coding, you got an occupational classification. So you got number in the major group, in the first major group, in the second major group, and you want to put a number, a confidence interval on that number. So I want to present this different approach in the main meeting.
Yeah, fair enough. in the first meeting, you were not here, and we mentioned conformal prediction. We mentioned PPI, prediction powered inference, which is if you are predicting a total, a mean, a quantile, a characteristic of the population, that I could give you a prediction interval for that population, and what you alluded to. I know you want to use the bootstrap to maybe estimate MSE or variance or so yeah. So this is in our work. So I don't have I don't have that PowerPoint in front of me, but we shared it with you, so you can check the PowerPoint. So we want to cover also that. And for conformal prediction, you can automate things, because usually these probabilities, we don't use them as such. We calibrate them first. And, we have colleagues here and we work on industry classification, for example, and you have hundreds of industries. And then our colleagues, they just order the probabilities and they take if the probability is over 95%, it's okay. Otherwise, there is a human reviewer and they don't calibrate, etc. So uncertainty is very important, that it gives you the length, the probability, and the length of the set. So you could automate that in a program to just filter out the cases you want to look at, like a human will look at. So it is useful, But for the other one, I would advise you. I will maybe advise to look at the PPI paper. I know Bootstrap, and we have colleagues doing that and this, but Bootstrap also has its weaknesses, So and you don't have guarantees. You don't have guarantees. You cannot use that estimate of the Bootstrap to give me a rigorous prediction interval. You have to do some asymptotics, or you have to do assumptions on the distribution and the way you use that. We can discuss next time, but maybe you should look at our first presentation. So this is for point estimation, point predictions, but we also have papers we want to look at, and we are going to look also at design-based conformal prediction, where we use the weights in conformal prediction. So that's the second paper. There is conformal prediction, there is design-based conformal prediction we want to look at, and there is prediction-powered inference, which is
Has anyone actually used conformal prediction among this group? Has anyone actually used conformal prediction to, say, classify occupational tax? No, but has anyone used, say, support vector machines to classify occupations?
Well, if I may, I'm Olivier Mélin from INSEE, the French National Statistical Institute. We are actually considering using conformal predictions in a regression case. Right now building a database.
I can actually see that conformal prediction is quite useful for quantile regression. But in official statistics, we rarely do regression analysis, do we? We just churn out numbers. Regression analysis, secondary analysis, analytical work.
No, it's not what I'm saying. We are building a database on housing wealth with a market value estimate for all dwellings located in France. And one question we have had for the past few years is, can we come up with a measure of uncertainty surrounding our estimate of market values, because those estimates are produced are computed with the machine learning algorithm, and we don't know how large the prediction, the confidence interval should be, and we think that conformal prediction might be the right methodological choice for in that use case. So I think there might be some use cases, but we should look for them quite precisely. But at least in my case, I have one precise use case in mind.
I think my presentation in May would hopefully cover your case, right? I am actually proposing a methodology to assess the uncertainty of machine learning generated statistics. So an example, which I keep on repeating myself, is like coding textual information from censuses into occupations. And you use a machine learning method like support vector machine or some other classifiers, right? Nearest neighbor, for example. So the method that I'm going to propose is, again, machine learning agnostic. So we apply to all types of machine learning methods. And it's also distribution free. I don't need to assume any distributions. I do not entirely agree with what Mohammed said when he said that Bootstrap requires distribution assumptions. No, I don't think so, because when you bootstrap, you're actually emulating the underlying distribution, even you don't know what it is.
I didn't say assumptions on the X. I didn't say assumptions on the X. On the distribution.
On what distribution?
I didn't say there are assumptions on the distribution on the X on your data. You are resampling, so it's.
No, I don't think so, right? But we can discuss it when I present it on in the next meeting. But I hope that my method would actually overcome. There's another thing too. My method would also be able to assess the bias of because when you do a prediction, you assign an occupation label. You sometimes you're right, sometimes you're wrong, but there could be a potential bias, and the method will also be able to assess that bias. So I'm actually trying to provide a mean square error, not just a variance.
Yeah, as I told you, we have on our list to look at the PPI paper. Maybe you should look at the PPI paper, which addresses the estimation of the variance and the construction of rigorous prediction intervals for estimates of machine learning models. We are going to look at it in this group, and I'm looking forward to your presentation. So I think next meeting will be a presentation by Xiuming. Amelina, I have a question.
Yes.
Is it possible? I don't know. In this group, we're gonna meet. We're gonna work on certain chapters. I don't have the last presentation here, but we're gonna look into certain chapters, and I was thinking for this group. Where is? Yeah, maybe what is the thing? Very fast. Can I share my screen again? Let me see. What is?
Okay. We have a hand too by Andrew.
Yeah. Okay. Go ahead.
I was just wondering if your prediction sets might be useful for generating multiply imputed data sets. So you could draw from, say you had a set of elements with probabilities, you could draw with probability of each and generate multiply imputed data sets, which could be useful.
Yeah. For imputation, you can Pontins imputation or like statistics in general, because you can use both PPI, also the framework PPI framework, if you are looking at imputing statistics. But this is like prediction also. I think it could apply also. Okay, it's my opinion. I don't know if somebody else has an opinion on that. I have here. I think for Xiuming, you were not here last time, and this is what we wanted to discuss, conformal prediction. This is for point estimation or prediction. And then design-based conformal prediction. This is the second thing we wanted to discuss. And then there is prediction power inference, which is a rigorous way to estimate variances and predict, provide rigorous prediction intervals for quantities like totals, like means, like quantiles, like other characteristics of the population. So we're going to cover that. And this is how we saw the work. Like we cover traditional methods, we do conformal prediction, we do design, we cover maybe this a little bit, design, and then we do PPI yeah, when you want to estimate the quality of estimates of characteristics of the population. So we have that in mind. So, but your bootstrap will be a good addition to this third one. Yeah.
So
Yeah.
Mohammed, it seems like there was some slides that you could not cover this meeting. Would you want to finish it up in the next meeting before Xiuming does his presentation?
It's okay if you Xiuming does it. I think I'm gonna just finish them because I haven't finished all of them. I can share them with the group and we can have discussion. Just my question for Amelina, I wanted, because we are gonna work together and then we are gonna divide into subgroups to work on certain chapters and contribute. So I was thinking, if one of us has a question, for example, are we gonna, as usual, communicate? We are not in the same institution, so it's pity we cannot use Teams or something. Can we have like somewhere a safe place where we can have kind of a blog, and where I can ask questions and colleagues can answer, and maybe a colleague can say question about this, and do you have a reference on this? And then we can maybe during the week, you know, have these discussions instead of waiting 1 month or writing emails, you know, like live. We can have them like daily if somebody can answer. I don't know if it is possible to have that somewhere.
Yes, so actually we had the task team before who create a channel, Teams channel where the external people can also edit. We will check if there is still possible because there's some IT policy change. We'll also check if we can do Slack.
Okay. Yeah, let us
Slack
know.
channel. Yeah.
That would be good. Like this, we can really, you know, you can ask your questions, and if colleague have time, can answer, and we can have discussions instead of waiting 1 month, 2 weeks to talk to each other.
Yeah.
You know. Yeah. Thank you.
I think
thank you all.
it's all.
Wiki too.
Can I just make another final comment? I think it's always good to begin with an end in mind. I think the end, I think in this case is there is a project assigned to us by XLG Moss, and I think it was Mohammed who proposed that project. So we have to first clarify exactly when we talk about uncertainty quantification, what exactly are we talking about? Are we talking about, as I was trying to advocate, that we provide an uncertainty to machine learning generated statistics? Are we talking about statistics putting uncertainty on official statistics generated by machine learning methods? Or are we putting an uncertainty quantification on individual predictions? So I think that's the very first thing that we need to decide. I am actually advocating that we are talking about uncertainty quantification on statistics, not on individual predictions. So I don't know how much time we have to finish off this project. If we go through those different aspects of conformity prediction, I think we'll probably see ourselves quickly run out of time. If we want to, let's say if we want to do uncertainty quantification on statistics, I think we should be picking that part of the conformity prediction suite that actually talks about putting uncertainties on means and population totals or quantiles. And so that's one thought. My other thought is that we can actually divide ourselves into maybe 2 or 3 groups, like one group pursuing conformity prediction work, another group doing PPI work, or another group doing the bootstrap work. And then you would have an output comprising 3 different approaches of uncertainty quantification. And then could be a final chapter to actually compare the pros and cons. And hopefully you can run some simulation, some real data sets, and apply all those 3 methods to the data sets and come up with, you know, empirical data to support one approach over the other. Then we're working towards producing something at the end of this project.
I think this is what we are doing. Let me share my screen again, because this is what we are. I think you were not here last time, Sumi, so you missed.
Yes, yeah.
So we have a wiki page here, so for us, and this is what we to answer your first question, we are doing both. We are doing both conformity prediction and assessing the uncertainty of statistics. We are doing both. That's what I mentioned before. So this is, we have an Excel sheet here, and we have divided, for example, people can put their names here. Some people are going to work on conformal, people can do design-based, people can do PPI. So we already organized that. And we want to do all of that. I know it is a lot. But we need to start, and maybe we can have an extension next year, because this is a lot of work. So we're going to do both point predictions, confidence prediction interval for point predictions, and we are going to do prediction intervals for statistics. And that's the PPI we're talking about, for example. I know there are works, I have colleagues here who use the bootstrap to estimate MSEs and etc. for statistics produced by machine learning models. We have that at StatCount. Some guys working on things like that. So
maybe we should invite them to give. We should invite them to give a presentation too, because if they're doing that work, so
yeah. So, but your work could be an addition to this part here, you know, where we are gonna predict or produce prediction intervals for statistics. So we could incorporate your work here. So you see, we already organized that last time, but we can organize it differently. Yeah. And that's why we divided it also. It's a lot of work. Sorry, somebody said something?
No, I just wanted to mention that people started leaving because we are running out of time. So maybe maybe Mohammed, you can share the presentation slides and people can have a look at it for their an individual time, and then come back to the point if they have a question, and the next meeting we do the CMI's presentation and so on. How does that sound?
Yeah, very good. I have to, they are not complete, so I'm gonna share the presentation as it is now, and then maybe I can add to the slides later. I didn't have time to do all of it, but I covered the regression and classification. Yeah, I will share it with Amelie now. Okay.
Maybe we will see if we can even upload this video so that people can revisit some of the presentation part, and then we will communicate through the email.
Okay, sounds good.
Yeah.
Okay, thank you everyone then, and see you next
time.
Okay.
Thank you.
Thank you.
Bye-bye.
Thank you. See you next time. Bye.
Thank you.
Thank you. Bye.
Thank you.
Goodbye.
Thank
See you next time.
That was very nice. Bye bye.